In this video, we're going to derive the pullback or vector-Jacobian product rule for neural ODEs, or you might also call it the final time integration of ordinary differential equations. We want to frame this integration as a function here with the arbitrary name q, which takes a parameter vector theta, an initial condition u0, as well as a final time capital T, and then it is given somehow implicitly through the solution to an ordinary differential equation, which is in terms of the unknown u, and has a right-hand side, which depends on u and the parameter vector theta. We will employ an ordinary differential equation solver. This could be an explicit time stepper, also with an adaptive time stepping scheme like a Runge-Kutta 4-5 scheme, for instance with the values tutu, dorman, and prince. This time stepper is then employed to start at the initial condition u0 and step all the way to capital T. The result evaluated at capital T is the output of that function. In terms of a neural ODE, your theta vector would be the weights and biases of the neural network that you use as the right-hand side to your ordinary differential equation. Your u0 is the input and your u at t is the output. In more scientific computing terms, where this is not necessarily a neural network on the right-hand side, you could, for instance, have some dynamics that are parameterized. So let's say, for instance, some material parameters like stiffnesses, E moduli, so Young's moduli, or something like this. In contrast to another task, which you might call full ODE integration, this one is just the final time integration. And I want to highlight this here once again, that we are only interested in the final time value. And that means not the entire trajectory. And as a reason, the solution at the final time, so the output of our integration, is a vector and not a function. So it has the same shape as the initial condition. It's an n-dimensional vector. Okay, that's the primal problem. So in terms of a neural ODE, this is the forward evaluation of this neural ODE, the solution to this ordinary differential equation. And for your scientific computing interpretation, this would, for instance, be simulating the dynamics of your system, which is parameterized by the stiffnesses and so on and so forth. But now you're not only interested in the primal problem, but also the backpropagation of tangents. And this is what we will be deriving in this video. So let me write down this task. So the task for this video is to backpropagate or backward propagate cotangent information on the output. And the output to that problem was u evaluated at capital T. So we will have u evaluated at capital T, but I will put a bar on top in order to indicate that this is a cotangent quantity. And this one will be of the same shape as the primal quantity, so it will be an n-dimensional vector. And we want to backpropagate this to the inputs. And the inputs are a cotangent parameter vector, which is p-dimensional. It is a cotangent initial condition, which will be n-dimensional, as well as a cotangent final time, which will be another real-valued number. The reason you might be interested in such a pullback rule or vector-Jacobian product rule that we are deriving here is if you want to insert this into a larger computational graph and then want to get some gradient information of a subsequent loss for which, for instance, the original primal input is involved. And more generally speaking, you might not be interested in all the cotangent outputs, but we will derive it for all of them here in generality. So let's say we could also only be interested in one or two of the three, and maybe let me also give them some meaning here. So if you have the cotangent parameter vector, this is usually relevant for neural ODE training, or if you are speaking in terms of the scientific computing interpretation, this might be for a parameter identification. Essentially both are kind of the same. Usually the difference is just that for neural ODEs you might have higher dimensional parameter spaces, whereas usually in scientific computing, it's just a handful of constitutive parameters. And just finding the analogy of classical neural networks to these neural ODEs is that those you also do some kind of backpropagation in order to obtain a gradient estimate and then fit your parameters using gradient descent. And this is kind of the analogy here. We will find an estimate on the parameter cotangent. Okay, then we also have the cotangent initial condition. So this could be, for instance, if it is part of a larger computational graph. So as part of a larger computational graph, that could, for instance, mean if you have multiple subsequent neural ODE calls, if there is an application for this, or you have in some sort of a residual neural network style, so where the neural network is called again on its own output, then you need to backpropagate throughout the entire chain. So there it's also relevant that we can go back to the cotangent on the input. And then we might also have some cotangent on the final time. This is a bit abstract. We will just derive it here for generality. Most often this is not too interesting. And then an important remark here, we want to do that without differentiating through the solver. So this is important. We want to do this without differentiating through, and the through is important, through the ODE solver by unrolling it. The idea behind this is that when we have the neural ODE that we have in our primal problem, this is usually just the abstract continuous level mathematical description of what is going on. If you implement that in your computer with your Runge-Kutta scheme, this will boil down to very simple computational operations. Addition, multiplications, vector addition, vector multiplications, and so on and so forth. By recording these operations in the style of what you would do for reverse mode automatic differentiation, you could also be able to just backpropagate through the operations of your solver to the implicit problem. And oftentimes this is a valid alternative. I will leave you some links in the comment section on a comparison between what we're doing here and this other approach. But here we want to look at this implicit problem as kind of an fixed supernode in our computational graph, for which we derive a custom pullback or a custom reverse mode rule. Okay, so let me go down here. This was saying we want to do this without differentiating through the ODE solver by unrolling it and applying reverse mode automatic differentiation to its operations. So as said, this is not what we want to do. Usually this approach is also called the discretize then optimize approach. So this is called the discretize then optimize paradigm. You also find this as DTO. I mean, right now we don't do any optimization, but the idea is that most of the time you want these derivative estimates to then do optimization. Here the idea is that you first discretize your ODE problem into some discrete operations your computer you understand, and then you optimize with the help of these discrete operations. But here we want to rather do, so here we want optimize then discretize. This is also called the OTD paradigm. And the reason it's called optimize then discretize is because we want to find a rule which will eventually turn out that we have to solve an adjoint ODE problem. And this adjoint ODE problem would then have to be discretized later on in order to actually solve it on our computer. So far so good. This is about the motivation of what we're doing. Let's now start deriving this very rule. And for this I want to start with the general pullback or vector-Jacobian product rule, which is that we will find the cotangent on an input, so let's say the parameter vector first, by taking the cotangent on the output, which is our cotangent on solution evaluated at capital T, and left multiply it with the Jacobian over which we want to pull back with respect to that very input. So here we have the Jacobian of our wrapper solver, so the call to the Runge-Kutta integrator or whatever kind of mechanism you want to use, and then multiplying this and contracting it from the left. I mean, it makes sense that we have to contract from the left, because if we take the numerator layout of that Jacobian, it will be n by p dimensional, and so we will contract from the left in order to contract the n dimensions of this primary state quantity, and then we are left with the p dimensions from the vector, which will then also turn out to be the same dimensionality as the cotangent on that parameter vector. And to be precise, this will give us the cotangent parameter vector transpose, because we are left multiplying a vector which is transposed with a matrix which gives us a row vector, but our cotangent vector of course is of the same shape as its primal counterpart, so it will be a column vector. In other words, we will apply another transposition here. And something similar holds for the other quantities, so we will find the cotangent on the initial condition by taking the final time cotangent, left multiplying it, so transposing it, left multiplying it with the Jacobian of the wrapper call with respect to u0, and something similar also for t. So we find the cotangent final time by taking u at the final time cotangent transpose and then Jacobian of Q with respect to capital T. Essentially what we are computing here is a vector times a Jacobian. So this is a vector. Let me first make some circles around this here. So this is all a vector Jacobian product. So vector Jacobian product. And commonly you would also find an alternative description of that by saying that we could also frame it as a Jacobian transpose vector product. So this is equivalent to a Jacobian transposed vector product. And for instance, that would look as that we have that the cotangent on the parameter is given as the Jacobian of Q with respect to theta in brackets transpose and then multiplied with the cotangent on the final time. So essentially we are just applying the transposition on both sides of the equation. Then we will get rid of the transposition of our cotangent on the parameter input. And of course this changes orders. And again, we can make sure if we have our numerator layout, which is n by p dimensional, and we transpose it, then the resulting matrix will be p by n dimensional. And then multiplying this with an n dimensional vector gives us a p dimensional vector, which is essentially the cotangent on the output. And also for later on, I think it is helpful to see that the Jacobian of Q with respect to theta is essentially the same as taking the Jacobian of the output of that function with respect to theta. So in other words, dq with respect to d theta is essentially the same as taking the derivative of u at final time with respect to theta. And the same, of course, if we take q with respect to u0, this is the final value with respect to u0, and the same is true for q with respect to capital T, which will be u at capital T with respect to capital T. And that kind of means here how strongly does the output of our function or our integration relate to the parameters which affect the trajectory, or for the neural ODE terms, with respect to the weights and biases. And here we will have it, how strongly does the initial condition affect the final position? And here, how strongly does the length of the integration interval affect this final condition? But be advised that this is a Jacobian, which will be a potentially quite high-dimensional matrix, and most likely it will also be dense. But for the reverse mode automatic differentiation, we never want to compute this Jacobian as dense matrices, but rather we want to do the vector-Jacobian product. So the naive way would be to compute that Jacobian and then contract it with the vector. But what we will find out is that we can write an alternative rule which essentially computes the result of the Jacobian being applied to the vector, or the vector being left multiplied with the Jacobian, without ever assembling or computing this Jacobian matrix. And I think this is a really interesting insight and speaks a lot for automatic differentiation. Okay, so far so good. Now we have these three individual vector-Jacobian products, and this again shows how composable automatic differentiation is, and I want to tackle them individually. So this will be component 1, then we will have component 2, and then component 3. Okay, let's start with point 1, which will be the parameter cotangent. So point 1 is the parameter cotangent, so theta bar, which will be a p-dimensional vector. Okay, how do we find the vector-Jacobian product for this? Let us start by writing down the ODE again. So the ODE we had as the implicit condition for the neural ODE, or for our final time integration, was that the time derivative of u with respect to t is the right-hand side function evaluated at u and theta vector. And as with many of these implicit problems, the solution to finding an alternative route towards the vector-Jacobian product is by taking the total derivative with respect to the quantity we are interested in of this implicit condition. And I also see there should be an underscore here. And now taking this derivative, so let's say we are taking the total derivative with respect to the theta vector. So we will take the derivative with respect to theta on the left-hand side, which is the time derivative of u with respect to t, and then on the right hand side we have the derivative with respect to theta on f of u and theta. Okay, let's start with the left hand side. And we see differentiation is a linear operation, so we can change the order and put the time derivative to be the outermost derivative, and then we will get the time derivative of du by d theta. And on the right hand side, we have to evaluate this total derivative. F has both an explicit and an implicit dependency on theta. The explicit dependency is obvious, and the implicit dependency is for u, because the u value, and this ODE is kind of thinking about this like on an infinitesimally small time sense, depends on theta, because theta effectively affects the trajectory of your solution to the ODE. So what we will get is, when we take the same order here, first the Jacobian of f with respect to u, then multiplied with u with respect to theta, plus f with respect to theta. Okay, cool. Now we found an expression for the Jacobian of the function with respect to theta, and this expression is essentially just another ordinary differential equation. And if you watch the video on the push forward rule, you might identify that we exactly used this ODE to then right multiply with a tangent quantity and identify the additional tangent linear auxiliary ODE problem that needs to be solved in order to forward propagate the tangent. But now we have to take a little bit of a different route. The reverse mode is always a little bit more tricky than the forward mode. And it works like this, in that we now take an inner product with an additional variable that, let's call it the adjoint variable. So we will take the inner product with an adjoint variable, and this adjoint variable is of the same type as our primary variable in the implicit problem, and this is u of t. So it will be lambda of t, a function of t, which maps from the real valued numbers to Rn. And if we go back to the primal problem, we saw that essentially we are only interested in the value at the final time. But in order to get to the final time, we will have to step through time, through the integration horizon, to then arrive at this final time. And this is also what I highlighted here. We solve the ODE problem for a hypothetical solution and then evaluate it at a time t equals capital T. On an implementation node, we will do not save intermediary values, because if you evaluated an ODE problem with a time stepper, you have the option to either just step through time and discard all the intermediary values, or save them at either fixed points or these points the ODE integrator choose to evaluate the right-hand side at. So in other words, although we are interested only in the vector at the final time, we will still have our time-dependent vector function, which is kind of an intermediate, and it's kind of hypothetical. And since we are speaking in this continuous case here, as we are following the optimized and discretized approach, I think it is reasonable to think of this hypothetical quantity as kind of something which appears in the mathematical consideration of an ordinary differential equation. And let me also put down this primal quantity I just talked about. So this essentially was that we had a u of t, which was a mapping from the real valued numbers to the n-dimensional vectors. So taking a time and putting it into a vector. Okay, now let's take the inner product. And don't worry, I will explain the inner product in a second. So essentially what this looks like is that we will have these angular brackets which indicate a functional inner product, or generally just any inner product in a vector space. And here we will have the lambda, which was our adjoint variable vector function, you might say. And then we will inner product this with the time derivative of this Jacobian, so d by dt of du by d theta. And on the right hand side, we will get something similar, that we will have the inner product of lambda with the Jacobian of f with respect to u multiplied with the Jacobian of the solution with respect to the parameter vector, and then plus another inner product with lambda and the Jacobian of f with respect to the parameter vector theta. Okay, what is this functional inner product? How can you think about that? And in essence, this is just a kind of a contraction mechanism, which means that this one, so the inner product of lambda and the time derivative of the Jacobian, can be seen as an integration over the domain, so in our case this is from 0 to t, of the contraction of these two quantities. So a lambda transpose, and maybe let me also indicate the time dependency here, transpose with the time derivative of the Jacobian, which will itself also be a function of t, and then integrated dt. So we will have a contraction in the sense of a vector inner product here, of that vector function with that vector function. And then we'll also have a contraction in that we will integrate out the temporal dependency. And therefore the result of this inner product will be something that is no longer a function of t. Okay, for now this might have seemed a little bit complicated. Why should we do that inner product with a quantity that just comes out of the blue? But as you generally see in vector-Jacobian products, eventually, as said, we're not interested in the full Jacobian, but a multiplication with it, and taking this inner product will get us one step towards that, as it already also suggests some sort of a multiplication here, which will then lead us, as said, to the final vector-Jacobian product. And for the next step, it is reasonable to think about it as kind of a way of us trying to avoid the computation of the Jacobian of u with respect to theta. So in other words, we try to find an adjoint problem, which is in terms of this adjoint variable lambda, which is selected such that we will never have to compute this du by d theta. This might seem a bit abstract right now, but I think this will become clear in a second. And in order to do that, we now need to make sure that this Jacobian u by theta stands alone. So here in that inner product, we have the temporal derivative applied to it. And here in that inner product, we will have the Jacobian of the right-hand side to the ODE multiplied with it. Okay, let's deal with it one by one. First, let's start on this left-hand side. And the way in order to move a derivative from the quantity to the other quantity, or in other words also the derivative inside of this integral, is to apply integration by parts, and by this we will move the ddt over to the lambda, and this works as this, that we will first integrate the quantity which has the derivative, so this will just give us the Jacobian function, and evaluate it at the limits of the integration, so this will be lambda transpose du by d theta, evaluated at t equals 0 all the way to capital T, and then importantly minus, and then again the integral from 0 to t of, now the derivative is applied to the lambda, so we will have the derivative of lambda with respect to t, in brackets, transpose multiplied with the Jacobian du by d theta integrated over time. And we see that the second part here is just another functional inner product. So we could also write, well, first we have the same boundary evaluation again, and then we have minus, and then this triangular bracket notation here with d lambda by dt, and then du by d theta. How nice, we moved the derivative over to the adjoint variable. Okay, let's write down the original expression again, but with our integration by parts done. So on the left hand side we will have minus d lambda by dt, the Jacobian of u with respect to theta in the functional inner product, plus, and then the boundary evaluation, so I just swapped the order here, this is lambda transpose times du by d theta, evaluated at t equals 0 and at t equals capital T. And then on the right hand side we still have lambda in inner product with Jacobian of f with respect to u, and then with u by d theta, and then plus lambda and Jacobian of f with respect to theta. Now we have to look into that function inner product. How can we move the Jacobian over to the other one? Okay, let's write this as in the integral notation. So we will have that lambda in inner product with the Jacobian of f with respect to u, and then the Jacobian of u with respect to theta is in essence the integral from 0 to t of lambda transpose df by du, du by d theta, integrated dt. And let us set some brackets in order to indicate what operation happens when. And if we translate that from here, we see that this is essentially a bracketing like this. So the adjoint variable is multiplied with the matrix product of that Jacobian with this Jacobian, but an equivalent bracketing would of course be to use that, and that we first evaluate the vector-Jacobian product here, which gives us another vector, and then this vector-Jacobian product. So we see that we could also move this Jacobian over here. So we will then have lambda and df by du, and of course we need our transpose here, and then the du by d theta. Maybe let me move the transpose a bit here. Okay, so we see that it is easy for us to move that over to the other quantity. Okay, now let's write this down once again. So we will again have the inner product, or the negative inner product, of the time derivative of the adjoint variable and the Jacobian we do not want, plus the vector-Jacobian product of lambda and the Jacobian we do not want, evaluated at 0 and capital T, is equal to the inner product of lambda transpose with f with respect to u, so a vector-Jacobian product, and u with respect to theta, and then plus lambda and df by d theta. As a next step, I want to look a little bit closer at this boundary, or our temporal limits integration, and let me write it down with the limits written out. So essentially what we have here is lambda transpose times the Jacobian we do not want, u with respect to theta, evaluated at t equals capital T. So we will start with the upper limit first, and then subtract the lower limit, which is lambda transpose and the Jacobian we do not want, evaluated at t equals 0. And if we do exactly this, we will figure out that the second term is 0, and that is because this term will be 0. And the reason for this is relatively simple, because we assume that our initial condition does not depend on the parameter vector theta. So this means that the derivative of u with respect to theta evaluated at t equals 0 is the same as the derivative of u0 with respect to theta, and this is what we assume to be the 0 matrix. And if we then left multiply a vector of the 0 matrix, well, it gives us the 0 row vector, but yeah, essentially this for us means it is 0. And this boils down that the temporal limits evaluation is just the evaluation at the uppermost point. Okay, let us write this down again. So we will again have the inner product of the time derivative of the adjoint variable with the Jacobian of u with respect to theta, and then plus, and now we only have the one evaluation left, so lambda transpose times du by d theta evaluated at t at capital T is equal to the inner product of lambda transpose times the Jacobian of f with respect to u, so the right-hand side with respect to the primal u, in the inner product with the Jacobian of u with respect to theta, the Jacobian we do not want, plus the inner product of lambda with f with respect to theta. So let's recapitulate to the point we actually want to arrive. So we're now in the situation that we found an expression for this adjoint variable, and we isolated the Jacobian as good as we can, such that it mostly stands for itself. But the ultimate goal of what we want to achieve is to find an expression for the vector-Jacobian product of the cotangent variable from the output with the Jacobian evaluated at capital T. And in order to do that, we will add an artificial 0 to our equation that we just found. So we will add an artificial 0. So add an artificial. This will look as follows, that we have u cotangent transpose with the Jacobian u with respect to theta evaluated at t equals capital T minus u cotangent transpose du with respect to theta evaluated at t equals capital T. And this will obviously be the 0 vector transpose. I mean, if you want to be super precise, but it will be 0 because we take the quantity and subtract it again from itself. But this quantity that we add here with this artificial 0 is essentially the result of the vector-Jacobian product that we want to have. So this is the vJp we want. Okay, and this will help us. So let's add this one, and then we will get a very lengthy expression. So on the left, we will still have our inner product of the time derivative of lambda with respect to t, the Jacobian we do not want, and then plus the upper limit evaluation with the adjoint variable, so lambda transpose of u with respect to theta evaluated at t equals capital T. And then on the right-hand side, we will have the first inner product of lambda transpose times the Jacobian of the right-hand side, and the Jacobian we do not want, plus another inner product of lambda with the Jacobian of the right-hand side with respect to the parameter vector theta. And then plus we will get the artificial zero. So this is the u cotangent transpose du by d theta evaluated at t equals capital T minus u cotangent transpose of the Jacobian u with respect to theta evaluated at t equals capital T. Okay, finally we are in a position in order to identify an adjoint problem. And this is a little bit of a self-fulfilling prophecy, but I hope it will make sense. So let's look at all the terms that contain the Jacobian we do not want. So here we have the Jacobian we do not want, here we have it as well, and then we also have it here. And also looking at it in more detail, so here we have an inner product over the entire trajectory. So here we would need the unwanted Jacobian at each point in time. Here we would need it only at the final time. Here we would need it at all points in time. And here we would need it twice at the final time. Ultimately, our goal is to find a description for the adjoint variable or a formulation of how to obtain the adjoint variable out of that such that these all will turn out to zero. But for the artificial zero, we will make a trick in that we keep one of these two entries. Let me call this, we will separate by the unwanted Jacobian. So the unwanted Jacobian, and that one was du with respect to d theta. And then we basically get two entries. So the one with the unwanted Jacobian. So here we will have minus the inner product of d lambda with respect to t, and then du by d theta, plus lambda transpose, then the unwanted Jacobian evaluated at t equals capital T. And on its right-hand side, we will have lambda transpose df with respect to u, and then the unwanted Jacobian. And then let's keep one of those, so we can choose either we will use the one with the plus or the minus in front. This will change a little bit the adjoint ODE we will get. Ultimately, taking either way is fine, because later on it will then cancel. But here let's choose the one with the plus. So we will have the plus u bar transpose du with respect to d theta at t equals capital T. And then we are essentially left with this expression as well as this expression. So we will get a zero. Probably it will be more precisely to have the row zero vector, but let's just have it as zero is equal to the inner product of lambda and the right-hand side derivative with respect to theta, and then minus u cotangent transpose du with respect to theta evaluated at t equals capital T. And now let's just call this quantity here theta bar. So this is the cotangent on the parameter, which ultimately is the result of the vector Jacobian for which we want to find this pullback rule. Let's extract a definition for the adjoint problem out of this first row. Okay, let me do that once again, kind of in the syntax here. So we will have a first stage, which will be the solution to an adjoint ODE. And this adjoint ODE kind of has two components here. So we see first we have some form of an equality in the inner product. So we have an inner product on the left, we have an inner product on the right. And then we also have some equality at the evaluation at the final time. This essentially means we will extract an ODE, an adjoint ODE, together with a terminal condition. So here we will extract the time derivative and we will get minus d lambda transpose dt, because of course in the inner product here it would have a lambda transpose, and on the right hand side we will get a lambda transpose df du. And we will get a terminal condition, which is that lambda transpose at t equals capital T. And of course, you have to be a bit careful. We will use capital T both for transposition as well as the length of our time integration. And on the right-hand side, we will get, this is u bar transpose. Or in other words, let's also be a little bit more precise. This is u bar at capital T transpose. Or in other words, this is the cotangent state on the output that we are given in order to perform our pullback operation. And then we have a second stage, which we can find by rearranging this expression, which will be a parameter vector bar is given according to the inner product of lambda and the Jacobian of the right-hand side with respect to. Okay, this was a bit quick maybe. Let me recapitulate again. So it's a little bit of a self-fulfilling prophecy, but we extracted an condition on the adjoint variable, which will be an adjoint ODE, which starts at the terminal point, which if we solve this, ensures that this equation holds to 0. And if this equation holds to 0, we essentially avoided ever to calculate the Jacobian, which is costly, dense, and unnecessary. So let me write this down. If lambda of t fulfills this adjoint ODE, we never have to calculate the expensive Jacobian, so let's also call it like this, the expensive Jacobian, and this Jacobian was du with respect to d theta. And we can also apply the transposition to both sides of the equation here to make that look a little bit nicer. So essentially what we will get is again our two-stage process. So first the solution to the ODE problem, which will be d lambda by dt. And let me also move the minus sign to the other side of the equation, is df by du in brackets transpose times lambda. And as the terminal condition, we will have lambda evaluated at t equals capital T is essentially the cotangent at capital T. And then we will find that the parameter cotangent is given as the inner product of this with respect to beta. Okay, let's use a similar verbal notation as we had it for the primal problem. So if we let me go all the way up here, you see that the primal problem was set kind of verbose here in that it is the solution to an ordinary differential equation. Let's say that we find the adjoint variable similarly. So, or let me also say that this is a two-stage process. Stage 1 will be that lambda of t is given as solve d lambda by dt is equal to minus df by du in brackets transpose times lambda for lambda of t over the time horizon. T is in 0 and capital T, or maybe also more precisely, we should say that this is kind of flipped here. It does not really matter here, but it has to be between capital T and 0 because it is a terminal value problem with the terminal value, and this terminal value is lambda at t equals capital T is u bar at capital T, so the cotangent we are given. And then the second stage is that we take the adjoint variable, which is time dependent, and contract it with the Jacobian of the right hand side with respect to theta, and then get our cotangent on the parameter vector. So we will get the cotangent parameter vector by taking the inner product of lambda and f with respect to theta. Or in other words, you can also say this is the integral from 0 to capital T of lambda transpose df by d theta dt. Or this could also be written equivalently. Probably this would even be transpose here. So I think this is probably loosely. So let me put in the quotation mark here. So probably better would be to write it as the integral from 0 to t of df by d theta in brackets transpose times lambda. So instead of writing a vector Jacobian product, we're writing a Jacobian transpose vector product. I think we can also remove these quotation marks if we put the transpose here, because that was quite clear if we go all the way up that this should not be theta bar, but more precisely should be theta bar transpose. And if we are that strict on the transpositions, then let's also say that left-hand side is the zero vector transpose. And I think I also saw that I forgot the minus sign here, which I even mentioned it, but I did not write it down. Great, now we found this two-stage process in order to obtain a parameter vector. And okay, let's finalize this and say here we will get the theta bar without a transpose as the inner product of f with respect to theta and lambda. So just applying transposition here again. But I think you still get the big picture, I hope. So let's discuss a little bit what we see here. And I think the first that we observe is something similar to what we also see in the push-forward problem, in that the auxiliary problems, in order to propagate tangent informations, are linear in their primal quantities. So here we have to solve an ordinary differential equation in terms of the time-dependent adjoint variable. And this ordinary differential equation is linear in lambda. So we will have a Jacobian matrix, or just a matrix, multiplied with lambda, and as such it is linear. So let's write this down. The adjoint ODE problem, or more precisely the terminal value problem, is linear in the adjoint variable. And that is nice, because our primal problem could have been nonlinear, and if you had a neural ODE, your forward problem is nonlinear ODE integration by design. Then you see here that your adjoint problem will be linear. I mean, the Jacobian matrix still has to be evaluated at the primal solution trajectory, so it will probably also change over time, which most likely will make the integration not as easy, but it is still not harder than the primal problem. And then I think an interesting other observation, now I see I forgot to delete the quotation marks, let's also do that now. And another interesting observation is that we put a lot of emphasis on that the primal problem is just the integration until a final point, and we will discard the intermediary values. But here we see, due to this two-stage process, that we will need the entire trajectory. So it is not just that we will solve the adjoint problem from the final time with the terminal condition all the way to t equals 0 and then take the value at t equals 0, but rather we will need it as the entire trajectory. So in a discrete sense, we will have to save it at intermediary values, because we then need to evaluate the functional inner product with the df by the theta Jacobian. And this, for instance, works if we imply a quadrature rule, so a numerical integration, which requires us to have the values of theta at the intermediary stages. So let me write this down, because I think this is a really interesting observation, and I also want to explain it in a second. So different to the primal problem, we do need the full trajectory of the time-dependent adjoint variable. So this was lambda of t. It is a function that maps from the real valued numbers, so from a time value to the n-dimensional vector space. So it has the same shape or output shape as the primal u, because of stage 2, which was the inner product with df, with the theta. And I think a nice motivation for this is that if we have the parameter theta, so let's go all the way up here to our primal problem again. So we will see the parameter theta is in the right-hand side to the ODE problem. So most likely it will affect the entire primal solution trajectory. So speaking in terms of the scientific computing interpretation, if you had different spring stiffnesses or E-moduli, your trajectory would be most likely a totally different one. Maybe not in these simple cases, but thinking in terms of the neural ODEs, if your weights and biases are different, then your trajectory will be different. And ultimately also your final point, which is the only one you're interested in, will be different. And as such, the parameter theta influences the trajectory at each point in time. Whereas in contrast, and we will also see that later, that the initial condition only affects it from the beginning. So it only has an impact from the beginning. Of course, the trajectory will be different based on different initial condition, but the effect of it is only in the beginning, whereas the effect of the theta will be throughout the entire trajectory. And as such, in order to get then an cotangent on the parameter vector, which is some sort of a derivative estimate, we need to collect all the contributions over the entire time that the theta has made to the trajectory. For me, it seems a little bit logical that we then need an inner product, or in other words, you can also think of it as a contraction over time, in order to accumulate all these influences that the theta has on the primal solution. Next observation is that in our problems, we will see vector-Jacobian products or Jacobian transpose vector products. So we will have that here, and we will also have it here, or more precisely, I think we will have it here. So essentially what those are Jacobian transpose vector products of the right-hand side to the original ODE. So once with respect to u and another one with respect to theta. And similar to the push forward, there are two approaches to this. So we could either use a reverse mode autodiff engine to obtain them. So by reverse mode autodiff. And if you use a neural ODE, that's probably the way to go, because they have certain structure that autodiff engines can easily exploit, and they are explicit, so it's easy to do. Or in a scientific computing term, it is also often that you have them by just knowing them, so by knowing. So because the ODE integration that is associated with certain partial differential equations has a particular structure which one can employ here, or which one can exploit here. And on top of that, for some ODE integrators, not necessarily the Runge-Kutta integrator, but if you use implicit methods, you might need the system Jacobian, so the df by du anyways. So you might already have a routine in order to compute that or get that available. So let me write this down. This is another node. It requires additional vJps, so vector-Jacobian products or Jacobian transpose vector products of the right-hand side of the primal ODE. So the right-hand side was that f, and this f was dependent on u and theta, and we need the vJps with respect to both of its arguments. They're now spending quite some time on deriving the parameter cotangent estimate. Let us now continue with the cotangent estimate on the initial condition. So this will be point 2. The cotangent on the initial condition. So it will be a u0 bar, which will turn out to be an n-dimensional vector, so it has the same shape as the primary counterpart. And if we are thinking in this neural ODE interpretation, the u0 was the starting point. Let's say, for instance, you use neural ODE to transform images, then this would be your input image. And then after the application of the neural ODE, you will get an output image. And now you have cotangent information on the output image and want to backpropagate it to this input image. And that could, for instance, be relevant, as we said earlier, if you had longer computational graphs and now want to use this cotangent information on the input some further down the line. So for instance, if you have a pre-processing stage, which is also somehow parameterized with, let's say, also a neural network, and you want to train both the neural ODE together with the pre-processing stage end to end, and then you might need these cotangent estimates. Okay, and the steps in order to obtain them are more or less the same for the parameter cotangent, so I won't go into them in that much detail anymore. We will start again with the ODE constraint. So we will take the ODE constraint, and if you recall, that was the ODE condition, so du by dt is the right-hand side, f of u and theta, that we also saw a couple of times before. And then the first step is to take the total derivative, and now we want to take it with respect to u0, because this is the quantity for which we want to find the cotangent estimate. So we will get the derivative with respect to u0 applied to the time derivative of u with respect to t is the derivative with respect to u0 applied to the right-hand side, f of u and theta. Okay, for the left, it's the same as before. The order of differentiation can be swapped because both are linear operations. We will get the time derivative of the Jacobian of u with respect to u0. And on the right-hand side, it's a little bit less obvious, but our u has a nested dependency on u0 because obviously the trajectory of u depends on the starting point. So what we will get is first a derivative of f with respect to u, which is a Jacobian we've also seen before, and then the Jacobian u with respect to u0. And of course, there is no further nested dependency through the parameter theta, so this is the only contribution we will get here from the total derivative. If you maybe recall from the video on the push forward, this would then be the point at which we right multiply with the tangent, obtain our tangent linear ODE problem, our auxiliary problem, and then integrate it in time. But for the adjoint approach or for the pullback approach here, we have to go a little bit of a different route as we've done before. And in order to do that, we will take again the inner product with an adjoint variable. It will turn out that this is the same adjoint variable as before, but for now, let's just assume it is another one. I will just give it the same name. So it is lambda of t, which will be a function mapping from a time to an n-dimensional vector. So it is similar to the primal unknown in the constraint equation. Of course, as before, we are interested only in the final state value for the neural ODE integration, but as a hypothetical continuous intermediary objective, we have the continuous time-dependent function. So then let's perform the inner product and we will get these angular brackets again. And here you have lambda and then the time derivative of our Jacobian u with respect to u0. And on the right-hand side, we will get the inner product of lambda and then df by du times du by du0. And we follow a similar strategy. We want to find an adjoint ODE problem in terms of lambda, which if it is fulfilled, we will never have to evaluate the dense, ugly, expensive Jacobian here. And in order to achieve this, we have to apply integration by parts on the left-hand side and move the Jacobian on the right-hand side. So we will do integration by parts, and here we will move the Jacobian. And by doing so, we will get something similar as before. So as said, I won't do the steps in detail because they are essentially the same except for just having a different denominator here. So from the integration by part, we will get minus the inner product of the time derivative of the adjoint variable. So we move the time derivative and the adjoint variable is now standing alone in the right entry for this inner product. But we will get a boundary or a limit evaluation of lambda transpose du by du0 evaluated, sorry, these are not the nicest brackets, at t equals 0 and capital T. And on the right-hand side, we can easily move the Jacobian over. So we will get lambda transpose df by du in an inner product with u by u0. And as before, let us take a look at the limit evaluation. So the limit evaluation is, so whatever is inside the brackets, evaluated at the upper limit minus evaluated at the lower limit. So we will get lambda transpose du by du0 evaluated at t equals capital T, and then minus lambda transpose du by du0 evaluated at t equals 0. And the second term in our case now will not be 0 anymore, but we can simplify it further. So let's take a look at it here and say we have lambda transpose du by du0 evaluated at t equals 0 is essentially the same as taking lambda, evaluating it at 0, transpose, and then multiplying it with du0 by du0. Because obviously if we evaluate u at 0, this is the initial condition. And now we are asking the question, how does the initial condition depend on the initial condition? That's the identity matrix. So we will get lambda evaluated at t equals 0, transpose times the identity matrix, multiplying something with the identity matrix. So we will just keep this row vector here. So this is just lambda evaluated at t equals 0 transpose. Okay, this is that expression. So let us write that down once more. So we will have minus the inner product of the time derivative of the adjoint variable with the unwanted Jacobian with respect to u0, then plus lambda times the unwanted Jacobian evaluated at the upper limit, so at capital T, minus just lambda transpose but evaluated at 0. And then on the right hand side, we will get the inner product of lambda transpose times the Jacobian of the original ODE right hand side with respect to u in the inner product with the unwanted Jacobian. So now we are at the point again where we have isolated the unwanted Jacobian as good as possible, and our goal is again to extract an adjoint ODE problem, but before we can do that, we need to add this artificial 0. So let me go up, and in the previous derivations, this was essentially, where do we have it? It was here, yeah, adding basically the vJp we want to evaluate. So in the very first one, we had the cotangent on the parameter estimate by taking the cotangent on the output and then multiplying it with the Jacobian. And now we basically have this vJp we want to evaluate. So we'll also take this as the artificial 0. Okay, let's add the artificial 0 going all the way down here and say we will add the artificial 0. And this artificial 0 was u bar transpose. So this is the output multiplied with the unwanted Jacobian du by du0 evaluated at capital T minus u bar transpose, same expression. So we are just adding something and then subtracting it again. Okay, let's write this down once more. It's a little bit cumbersome, but we are getting towards the finish line for this derivation. So minus the inner product of the time derivative of the adjoint variable, then du by du0 plus lambda unwanted Jacobian evaluated at final time minus lambda transpose evaluated at starting time. And on the right hand side we will have that inner product, so lambda transpose df by du and du by du0, and then our artificial 0. I don't think it will fit in that line anymore. Let's try. So we will have u bar transpose du by du0 evaluated at t equals capital T, and then minus u bar transpose du with du0 evaluated at t equals capital T. Okay, this is now in the form of us being able to extract the adjoint ODE problem, but let me remind you again of what the goal is. We will select lambda of t, or more precisely, we will select an auxiliary problem such that we never have to compute, assemble, integrate, however you want to call it, this du by du0 Jacobian. And as such, we can extract, maybe a little bit different than we have done it before, we can extract the things that have to hold over the integral, so, or over the trajectory. So we will have contributions that come from over the trajectory, which will be that we have a minus d lambda by dt in the inner product with the unwanted Jacobian is equal to the inner product of lambda transpose df by du by du0. Then we will have contributions at final time. So these are the contributions we see here and as well over there. But we will again make the trick that we will only choose one of the two. And it's again reasonable to choose the one which has the plus in front. So we will get lambda transpose du by du0 evaluated at t equals capital T is u bar transpose du by du0 evaluated at t is capital T. And I think I forgot the transpose here. Of course, yeah, there's a lot of things I should be keeping in mind here. And then basically we have a leftover, and the leftover will be just that one here and one of the two from our artificial 0. So we will have a minus lambda transpose evaluated at t equals 0 is equal to minus u bar transpose du evaluated at u0 at t equals capital T. Okay, I said this is a little bit of a different approach to the extraction that we did with the parameter cotangent, but again, it allows us to identify both an adjoint terminal value problem and a second stage evaluation, which then actually gives us the vJp result or the cotangent we want. So we will get that we have the adjoint TVP, that's a terminal value problem, given as, let's again put the minus on the other side, apply the transposition similar to before, and we will get d lambda by dt is minus df by du in brackets transpose times lambda. At the terminal condition, we will again get cotangent contribution from the original primal's output. So we will have lambda at t equals capital T, essentially u bar evaluated at capital T, which we are provided with. This is again a terminal value problem, giving us a lambda trajectory. And then we have, or maybe if we call that stage 1, and then we have as stage 2 the evaluation, which will basically tell us, if we do the transposition, we will then see that du by du0 in brackets transpose times u bar at capital T, which essentially is the tangent contribution on the initial condition, is the variable evaluated at the first point. And let me write this down once again a little bit more verbosely so that we get lambda of t by solving an ordinary differential equation. This d lambda by dt is minus df by du in brackets transpose times lambda, or lambda t. And here again, let's also be general. Again, we want the full solution for lambda. So let's say again over t, element of capital T to 0, with the terminal condition being that lambda at t equals capital T is u bar at capital T. And this should look familiar, or maybe let me do this again, this is stage 1. And this should look familiar. This is exactly the same adjoint problem as we found it for the parameter cotangent. Let me go up to where we did that. Where do we have it? Here. So it's the same right-hand side. So it is again the Jacobian of the original problem's right-hand side, transpose applied to lambda, a minus in front, same integration limit, same terminal condition. So the only thing that differs in order to get the cotangent on the initial condition is the second stage. What I find also very interesting is that here we argued that we need the inner product because the parameter affects the solution trajectory over the entire horizon of the solution trajectory, but the initial condition only affects the solution trajectory. I mean, it affects the entire solution trajectory, but it only affects it from the start. I mean, this influence will of course propagate throughout time, but it's not like refreshed. So there's no new input from the initial condition at later stages throughout the integration. And as such, we will also see that we get the cotangent by just evaluating the adjoint variable at the 0 time. And I think this is an extremely beautiful insight. So if you are just interested in the cotangent on the initial condition, there is no need to save the full trajectory. It would be totally sufficient to just step through as you would do it with your primal problem, just in the reverse order. And we will see later on that it's not that easy because you still might need some saving, but in general, just from this purely theoretical point of view. And this is something I think extremely beautiful. Okay, but it's a lot of talking, but let's write it down again. So let me note down these observations we can do here for the adjoint problem. So we can note down this is the same adjoint terminal value problem as for the parameter cotangent. And side note, this is to be expected because whenever we have vector-Jacobian products, our workload kind of scales in the number of outputs. So here our original function q only has one output, but it has 3 inputs. So the two cotangents on parameter and the initial condition, which both have auxiliary ODEs, we will soon see that the final time contribution is rather trivial, but those share the same ODE. And this is kind of maybe philosophically expected here, but nevertheless. So this is the same adjoint terminal value problem as for the parameter cotangent. And now crucially, with the difference that we only need the adjoint state at t equals 0 to get the cotangent on the initial condition. Since it is a similar adjoint TVP, we will see we again have our Jacobian transpose vector products here. So we will have the Jacobian transpose vector product here that we also saw for the parameter cotangent. And again, two strategies, either using reverse mode autodiff or by just knowing this Jacobian. Okay, then let's move to the last cotangent we have to find, which is on the final time. Often not too necessary, but we will just have it here for completion. So this is point 3. This is the cotangent on the final time. So this will be t bar, and it's another real valued number. So if you think in terms of like sensitivities or gradients, then this might give you some information on whether you have to either increase or decrease your integration horizon. And in order to derive this, we will take a little bit of a different route. We will use the probably a little bit abstract general result to ODE integration, which is also the approach we took in the push forward derivation. So this is the general result to ODE, ordinary differential equation integration, in that we find that the solution u at t, which was the output of the primal path, is given as u0, our initial condition, and then an integral from 0 all the way to capital T of the right hand side of u evaluated at t, as well as our parameter vector theta, and then integrated dt. Let's take the derivative of this expression with respect to t. So we will take the derivative with respect to t, or in other words, the derivative with respect to the length of the integration horizon. So this will be the derivative of u at capital T with respect to capital T is equal to the derivative of the initial condition with respect to capital T, plus, and then the derivative of an integral where the t appears in the upper limit of integration. So in that case, it is not part of the integrand, but it is rather part of the integration limits. And we know if a variable appears in the integration limits, but not in the integrand, and we take the derivative with respect to that, we can just evaluate the integrand at that very position. So essentially this derivative will boil down to the right-hand side evaluated at u at capital T and theta. We will plug in the u at capital T from the primal solution. Okay, then let's take a look at that. We here have the derivative of the initial condition with respect to capital T. So how does the initial condition depend on the length of the integration horizon? And that is of course 0. So there is no contribution from that part here. And as such, we will find that the, in quotation marks, Jacobian of the output of our primal pass with respect to the capital time is the right-hand side evaluated at the primal output and the concrete parameter vector theta. But if we then go up, because we want to find the cotangent contribution, or in other words, the result of the vector-Jacobian product, and it's been some space here already, so this is 0.3, where we will then have to left multiply with the cotangent information on the final state, and thereby then contract the dimension in order to go back down to a scalar. So let's do that. So let me go down all the way again to what we just derived. So we are here, and now let's say we are interested in the vJp or vector-Jacobian product. So what we will do is that we will left multiply the Jacobian with the cotangent information. So u bar transpose, so u bar at capital T transpose, and again be careful, we're using the T twice, with the Jacobian of u at capital T with respect to capital T is, well, u bar transpose at capital T multiplied with the right-hand side function evaluated at the primal output and the parameter vector theta. And be a little bit careful, I don't use an underscore for that function here, but that is of course a vector valued function, so it maps the state and the parameter to the state. So the output is a vector which is of n dimensions, and if we then take the left multiplication or some form of an inner product with a vector of the same size, but this one has the cotangent information, this will then contract to a scalar. This will give us the cotangent on the final state. And as such, we also know that this inner product is symmetric, so we could equivalently also write that this is f evaluated at u at capital T and theta transpose u bar at capital T. So it is just the inner product. Okay, now we have found cotangent informations on all the three inputs to our original function. This now allows us to write down the full pullback rule. So the full pullback rule, which will be a bit high level, but technically this is what you would then implement into your autodiff engine. And the idea is that we will find the backward rule on the integration Q. So again, recall that we had this wrapper function Q, which is given as the evaluation of our neural ODE by integrating it from 0 to capital T, let's say for instance with a Runge-Kutta 4-5 scheme. This one takes primal inputs, which are theta, u0 and capital T, a parameter vector, so in a neural ODE, the weights and biases of the network, or in scientific computing, some constitutive parameters, or something else, whatever kind of parameters you can think of. Then u0, the starting point. Obviously, if we have a time integration, we need to start somewhere. Then we have our capital T, which will be the length of integration horizon. Most of the time for neural ODEs, one sets this to 1, but this could also be the case that if you have a more physical interpretation of what is going on, that this is actually something in seconds or of that kind. And additionally, we provide the pullback rule with a cotangent information on the output. So we have a u bar at capital T, which we're also given. It has the same shape as the state. So it has the same shape as u0. It has the same shape as u at capital T. And then what does our pullback rule do? So first it evaluates the primal. So it does Q on theta, u0 and capital T. By doing so, it will give us the original primal output. So this is u at capital T without a bar on top. And then it will give us cotangents on all the inputs. So it will give us a cotangent on the parameter vector. And recall that one was given as the inner product of the Jacobian of the original right-hand side with respect to theta and the adjoint variable lambda. So this will be our theta bar. And as such, it will be again a vector, no longer a time dependency, because this inner product integrates out the time dependency of both this Jacobian as well as the adjoint variable lambda. Then it will also give us the cotangent on the initial state, which is just the adjoint variable evaluated at 0.0. So this will be the cotangent on the initial state. And then also, in case one is interested in that, we also have the cotangent on the final time, which will be f evaluated at u at capital T and theta. So this is the u at capital T from here basically. And then this is in an inner product with the u bar at capital T. And these are basically the three pullbacks that we have. And as said, this will give us the cotangent final time. Let me put a nice box around this because this is the major finding of the video. This of course leaves out the detail on how to obtain the adjoint variable, but we know this is the adjoint terminal value problem. So with the adjoint terminal value problem, and recall that one was given that lambda of t, so the full trajectory on our adjoint variable, is given as the integration, so we say integrate, of the adjoint problem, which was d lambda by dt is minus df by du in brackets transpose lambda, so a Jacobian transpose vector product, with lambda at t equals capital T being given as u bar at capital T over t in capital T to 0. So it is a terminal value problem. It starts at the final time and we integrate it all the way to the beginning. So here in our problem, we chose that the integration starts at 0. And this is more or less it as you would find it in these continuous derivations, but I think it leaves out a lot of computational details, because based on this problem description, there are now a lot of ways in order to tackle actually implementing this. And this is what I would now like to do in a last section on computational considerations. So let's say computational considerations. In the beginning, I just want to repeat a little bit of what we already summarized in the individual cotangent contribution sections. First of all, this is the rather trivial observation. If we are only interested in the cotangent on the final time, for whatever reason, then we don't need an adjoint problem at all. So if we are only interested in t bar, no adjoint problem has to be solved. And if you watch the video on the push forward rule, then you know that this is also the case if we wanted to get some tangent information propagated from a t dot. So this is similar to the push forward rule. So this is similar to push forward rule, which I think is an interesting observation, that in that particular case, they kind of share the same way of how to propagate or backpropagate tangents or cotangents respectively. Then also an interesting observation we made is that if we are only interested in the U0 tangent contribution, so if only interested in U0 tangent, we do not need to solve for the full trajectory. So we do not need to solve for the full adjoint trajectory. So this is the lambda of t, so lowercase t, which goes from capital T all the way to 0. But alternatively, we can do something similar to the primal problem, but just reversely in time, that we just let the ODE integrator step through as fast as possible. We don't need any intermediary points. It can do as many tricks as it wants, as long as it arrives at the t equals 0 point again and does so reasonably accurate. So, but can ignore intermediate or intermediary values and directly step from t equals capital T to t equals 0. And as said, this is similar to the primal problem. And of course, this only holds if your primal problem was also a final state integration. As I also said earlier in the video, you could also be interested in the full ODE integration, where you would want the full time-dependent function, then this of course would not hold true. So similar to the primal problem, but the primal problem of course does it in the chronological direction, so like in increasing time direction, but here for the adjoint, we go reversely in time. Then as a consequence, of course, for the cotangent parameter, we need the full adjoint trajectory. So we need full adjoint trajectory. And I thought of kind of motivating this, at least this makes sense to me, hopefully it also does to you. This is because theta bar, so the original parameter vector theta, also influenced the entire primal trajectory. So we need the full lambda of t, of course, in order to evaluate the inner product, and then, for instance, use some numerical quadrature rule in order to evaluate that integral. And then, of course, the last, but probably from a pragmatic point of view, the most important one and also probably the most difficult one to implement is that we need to evaluate vector-Jacobian products or Jacobian transpose vector products. So the df by du in brackets transpose times lambda, which is equivalent to lambda transpose df by du, so either Jacobian transpose vector product or vector Jacobian product. Loosely speaking, of course, this would need a transposition, so maybe let me put this like this. And the other one, which was df by d theta in brackets transpose times lambda, which was equivalent to lambda transpose df by d theta in brackets transpose. So the auxiliary vJp's that appear both in the adjoint problem as well as the final evaluation for the parameter cotangent can be evaluated by reverse mode autodiff. Okay, we already said that, but this left out one really important aspect, that if your function is highly nonlinear on u and theta, the vector Jacobian product or Jacobian transpose vector product will still be a function of u and theta. So in order to evaluate that, we need values from the primal trajectory. So let me write this down, that in general, so of course if you have, let's say, linear ODEs or something, then this might not necessarily be too troublesome for you, but in general, if you have highly nonlinear ODEs, as you would have it for neural ODEs, you would require the primal solution trajectory. So in general, this requires the primal, or let's also say the full, in order to indicate that, primal trajectory. So this is the u of t, with t being from u to 0, which is actually something we did not want to save from the primal execution. So because in the primal execution, we just want to step through. And similar to also to classical multi-layer perceptrons as neural networks, if you just want to have a forward pass, you don't want to save your intermediary states. But if you want to do backprop, you need to have them saved. And I think this is a little sad, right? Because it is not what the primal pass did. But what can we do about that? And there are two major approaches to this. The first is in analogy to what you would do in classical neural networks. And the second one is an interesting trick, which was also shown in the neural ODE paper. Okay, approach number one is to save the primal trajectory and interpolate. So save primal trajectory and interpolate. So what do I mean by this? Let us look at a simple example. So let's say we have the time axis here, and let's say here's our point 0, and there's our point capital T. And then we have here our u, then this position is our u0. Well, I think I should remove this underscore because we are no longer having a vector here. So this is just a scalar problem. And then we solve the trajectory with our integrator. So maybe the trajectory looks something like this. And this will then be our u at capital T. So this is the output of the primal integration. And the orange one, this is the trajectory. And now let's assume we have maybe a second bar here, which is the adjoint variable lambda. And this integration starts at a certain point here, which is, let's say, the cotangent on the final state. And then this integration follows the adjoint dynamics. So this will be maybe something like this, and then ends here at lambda at t equals 0. So this one is the adjoint trajectory. And in order to evaluate the dynamics, so let's say, for instance, you have your ODE integrator, and your ODE integrator say, okay, hey, I'm now at point, let t be 1, and let's say, hey, I'm now at point 0.9. Please evaluate the right-hand side of your adjoint ODE problem. And okay, let's look at this. The right-hand side of the adjoint ODE problem was the Jacobian transpose vector product. And then, okay, you go into your autodiff engine and say, okay, please evaluate my Jacobian transpose vector product. And then the autodiff engine says, okay, please give me the primal values. So it then needs also, in order to get the dynamics here, it also needs the primal value. Maybe let me choose another color from here. So it needs this information. Okay, how can we get that information? And now the idea is basically that we will take our primal integration horizon and maybe do some stepping here, some equal distances, for instance. So this, let's say it be 0.1, 0.2. Well, I did not check if that matches, but I think you get the idea. And then basically we will save the values and keep them in memory. And now let's say we are here at these, we have two values, and then we can just basically interpolate, also with a linear interpolation, and then get this information. But as said, this is in contrast to our actual primal problem. So in order to use that approach, we had to modify our primal pass. So the primal pass will no longer be stepping through, but will actually be stepping through and saving values. And of course, this is also a little bit heuristic because we need to know at which point we need to save. It depends a bit on how highly frequent the dynamics is, maybe how many points you need to save and how value approximation needs to be. It all depends a little bit on the particular application, but I think this maybe should get the picture across. And as said, this is an analogy to what you would do in classical neural networks, in which if you're only interested in a forward pass, you could just step through. But if you want to do forward and backward pass, you would save your intermediate states. With the difference that for classical neural networks, you wouldn't have to interpolate because you always have discrete steps, but here we have some continuous time. So for instance, our adjoint time stepper might require the dynamics being evaluated at points where we did not save the values from the primal pass. So this is the first approach, save the primal trajectory and interpolate. And we could also do this possibly with checkpointing. So possibly with checkpointing. So this would be making it a bit more efficient, so on. So instead of interpolating with like a linear interpolation, we could maybe rerun the dynamics from that point on with the original primal. There are a lot of tricks one can do, but essentially we still need to save a little bit. And the second one, it's an interesting one, but it also has its limitation, which is to run the primal problem reversely alongside the adjoint problem. So the second point is to run the primal problem or integrate the primal problem alongside the adjoint problem reversely in time. Okay, well, how does that work? Let us again look at the same diagram. I will draw that one here with the time axis. And then here we have u. And again, we will have it from 0 all the way to capital T. Then we have our starting point. Let's say that is u0. And then we will do our primal trajectory. Let's do it like that one here. And we will end up at u at capital T. And we will do it in the same way as we would do it just in our primal pass. So we'll just step through, no saving. We will only arrive at our final time. And then again, we want to get our adjoint. So we have here a lambda axis, and let's say our adjoint starts here. Okay, I think I used different endpoints. Maybe let's have that consistent. So let me maybe change that a bit so that we can get that consistent. So let me again use the dynamics of the primal pass. So that was kind of looking like this. Here's our u at capital T, and then we started with the cotangent value here. So this was the terminal starting point for the adjoint ODE problem. And now you want to integrate that. Well, you do your first dynamics, and now your adjoint ODE solver, your Runge-Kutta scheme, wants to query the dynamics at that point. And in order to get that, you will run your original ODE problem also backward in time. So you will run it again, and you might end up at that point, and then you can use that information in order to evaluate the dynamics, and then go on. Let me check what was the dynamics. So kind of something like this. So you get here, and then your integrator might want it again, and you step all the way here and use the information. And I think you get the point. And by doing so, we can also get the adjoint position. I think we ended up somewhere here. Yes, so this is then lambda at t equals 0. And I hope you get the point. So we let the primal problem run again backward in time. So we go forward and then backward in time. And hopefully this should then, if we do it right, somehow end up again at this point. So it will be a little bit off because we have some rounding errors and so on and so forth, but it should work. And at each point we can feed the adjoint dynamics with the primal trajectory. And since we run it in the same direction. And if you recall from the push forward, we could also assemble one large ODE system in which we would run the tangent linear dynamics next to the primal dynamics to always feed them with the information that is relevant for evaluating the additional Jacobian vector products, but here for our vector-Jacobian or Jacobian transpose vector product. And this is also what was shown in the neural ODE paper. So this is essentially from the neural ODE paper, and they call it the O of 1 backprop in memory. Or so let me say O of 1 backprop in memory, because in classical neural networks, your backprop is of course computationally as expensive as the forward pass, but you need to save all the states, whereas in the forward pass you can just step through. So it has a scaling in the number of intermediary layers which you need to save in memory. And here this has an O of 1 property because you can step through the primal problem, get at your final point, and then run the primal problem backward in time. But it definitely has its issues because there are a lot of situations where if we run the trajectory forward and backward, we do not end up at the same point. If you are aware of nonlinear dynamics, you know that chaotic systems exhibit a property that if we slightly change the initial condition, over some period of time, they will divert exponentially. So especially for chaotic systems, this is really hard. And since our neural ODEs turn out to be highly nonlinear dynamics, there is a good chance that this one will not work. But of course, will not work is a spectrum. Even if our point at which we end in the end is way off, maybe it is still good enough to feed the dynamics. So it's really hard to say. There are some investigations on that. I will leave some links in the video description, but generally you have to be careful. It is not a free lunch. So let me also add that remark. This is only possible if the right-hand side dynamics are not chaotic. Or even if they are chaotic, our integration horizon needs to be certainly below the Lyapunov exponents range before the system kind of explodes into chaos. So it's a little bit problem dependent. But I hope this was an interesting insight into that. This is in how we can evaluate the vector-Jacobian products, but we have one last point, because now even if we do avoid saving the primal trajectory, we still need to save the adjoint trajectory, because recall the evaluation for the cotangent parameter state required us to take the inner product. Well, is there even a way to avoid that? So let me frame the question that we have one last computational consideration, that for theta bar, we need to evaluate and this is important, this is a functional inner product. So in essence, we will find that theta bar is given as the inner product of df by d theta and lambda. So it will be the integration from 0 to t of df by d theta, which of course will also be time dependent because we need to evaluate it at the primal state, and together with the lambda, which will also be time dependent, and then integrated dt. How can we avoid this? And the trick is also coming from the neural ODE paper. But first, let me write down the first approach, which we could also do as an alternative to the one that is presented in the neural ODE paper. So this first one would be that it can be done after obtaining the full adjoint trajectory. I said, so maybe if we would have used the first trick and have avoided saving the primal trajectory, but now we saved the purple trajectory at certain points and then evaluated the quadrature afterwards. But this is also not what we'd want to do. So because that's also a little bit sad here, because it would also require us to save that in memory. Before I go on, let me just add one more remark that, of course, this is only relevant for theta bar. So if we are only interested in u0 bar, so the cotangent on the initial condition, as said, we could already step through. So there we wouldn't have the headache because it didn't require a functional inner product. Okay, long story short, what is the solution that they present in the neural ODE paper? And the second one is with solving an additional ODE problem also reversely. So I think I also see here that this should be a transpose. Okay, how can we motivate that? So let us look at the integral, and we will see that the integral from 0 to t of df by d theta in brackets transpose times lambda dt can also be written as minus the integral from capital T to 0. So we change the limits of integration of the same integrand, df by d theta t at lambda dt. Okay, let's have that. And let's add a 0 here and say this is equal to 0 minus this integral from t to 0 of df by d theta transpose lambda. And if we look at that, I mean, it might not be that obvious at first, but this reminds of the general solution to an ordinary differential equation. So we used that once when deriving the cotangent on the final state. So where did we have it? And that we say that the solution of the primal path, so the value at the final time, is the initial condition plus integration from 0 to t of some dynamics. And now we basically have, so let me go down again. So now we basically have an terminal condition somehow, then some dynamics from t to 0, and this will give us the cotangent parameter value. So we can solve that with an auxiliary ODE problem. So okay, so I had a little crash in the writing program because the file is getting too large. Obviously, the video is also getting quite long. Props to you if you're still with me here, because it's a lengthy derivation and there are a lot of details, but I hope I can present all the details in the necessary depth. Okay, well, but we looked at this integration and we saw that this reminds us of the general solution to an ordinary differential equation. And we can also write this in the verbose notation we also used before, and that we have theta bar in that sense is given by saying we integrate a dynamics, which is now in terms of theta bar dt by its right hand side is minus df by d theta in brackets transpose times lambda with a 0 terminal condition. So with theta bar at t equals 0 being the 0 vector, and we want to integrate that from t equals capital T all the way to t equals 0. And by doing so, we can kind of step through again. This kind of does not require us to use a quadrature rule, and by employing the ODE solver, the Runge-Kutta 4-5 scheme, we kind of accumulate the integration over time. So we just avoided another saving, because if we run that together with the primal ODE backward in time and together with the adjoint ODE primal and backward in time, we always have the primal and the adjoint state to feed that integration. So let me also give you the highlight here again. So we will have time, and then here let's have u, and let me maybe indicate again the 0 point and the capital T point. And now we have our starting points. This is the initial condition, and then we integrate the dynamics to get our final point, so u at capital T. Then we will start at that point again and integrate backward in time. Well, of course, we do not do this separately, but we do it alongside an integration of the adjoint variable, which starts at the cotangent final state. And then I think we had some kind of a dynamics like this, and then we will end up at lambda at t equals 0. And this lambda at t equals 0 is the cotangent on the initial condition. And we get that dynamics by feeding this one here into the adjoint trajectory. But now we have another ODE, and I promise you this will be the last one, which will be the ODE on the theta, which starts at 0. So here we have, let's say, theta bar at t equals capital T will be 0. And then this also has some dynamics. Let's say, for instance, it has this kind of dynamics, and then adds up here at theta bar at t equals 0. And this is also the theta bar we want. So the theta bar we want. And in order to get that, we have to both, and now the arrows are getting a little bit crazy, but we have to both feed the primal trajectory as well as the cotangent trajectory, because the vector-Jacobian product that we have here, or the Jacobian transpose vector product, needs the primal information, but then we are multiplying it with the current adjoint value. So maybe let me add one more point. So here we have that one and this, but I think you will get the point. And essentially this trick of also avoiding saving the adjoint variable is what is done in the neural ODE paper. And essentially what this then allows us to have an ODE system consisting of 3 separate ODEs running backwards in time. And this is what I want to finally write down. And for this here, I changed into a new file because I'm getting issues constantly with my writing software. So let's go here again. And this idea from the neural ODE paper is then basically a 2-stage process. So the first stage is we will solve the primal problem. So in a sense, we will start at u0, and then we will add the parameter theta as well as the capital time in an integration process, then giving us the solution at final time t. And then the second stage is to solve 3 ODEs backward in time. So basically this means we will use this final value we got from the primal path, so that one here, and have that again. So we will have u at capital T, so there's no bar on top. Let me remove this problem here and integrate that back. So this will then be approximately the initial condition, hopefully. And then we will have a u bar at capital T, for which we will use the adjoint dynamics to get the lambda at t equals 0. And then we will have a theta bar at capital T that then integrates to theta bar at t equals 0, which is the theta bar we want. So this one starts at 0 and this one starts at the very cotangent value we give. So this is the primal problem reversely in time. This is the adjoint problem reversely in time. And I would maybe call this is the quadrature, so the numerical integration of an integral problem backward in time. And we can also write that down in a joint ODE system, in that we integrate, so d by dt, of the joint degrees of freedom, which consist of the primal, which is u, then the adjoint, which is lambda, and the cotangent on the parameter is given by the following dynamics. So the dynamics on u is of course the original dynamics of the right hand side, so f of u and theta. Then the dynamics on the adjoint variable are given by the Jacobian of this right hand side with respect to its first input, transpose applied to lambda. And here the dynamics are given by df by d theta in brackets transpose times lambda. And it is a little bit important to look at what are the unknowns in the corresponding ODEs. So here the unknown is u, and therefore it appears here as well. There the unknown is lambda, and it appears here, but here the unknown does not appear on the right hand side. So this quadrature problem is essentially just an integration, right? So we want to avoid computing the integral, so there is no theta bar on the right hand side anymore. And in order to solve these vector-Jacobian products, we feed the value here, and then in order to solve the quadrature problem, we also have to feed the adjoint variable here. And if this is put together into one large dynamics, it can be solved jointly together, and we never have to interpolate or save value. So this is then also our O of 1 backprop in that sense. This will be with the terminal condition. So with terminal condition, which is as follows, that u, lambda, and theta bar at t equals, sorry, not 0, but at capital T. I'm sorry, I also forgot that here there should be a minus, of course. So these are negative. That's really important. Okay, but the initial conditions are that for u, or terminal conditions, sorry, the initial conditions of an ODE integration reversely in time, it's totally mind-bending, but it's also been a long video now. Okay, but the terminal condition for u will of course be the u at t, which comes from the primal path. Then for lambda, it will be the cotangent on that, which we are just provided with. And for this, it will be the 0 vector. three ODE problems. One's the primal, which is a nonlinear problem, then the adjoint problem, which is a linear problem, and then the quadrature problem, which is, you might say, a constant problem. So they are decreasing in difficulty. And this is essentially what was presented in a neural ODE paper. First solve primally with your neural ODE, then solve this auxiliarily augmented dynamics and get both the cotangent on the initial condition as well as the parameter. So we will then get that U0 cotangent, as said, was the adjoint variable evaluated at the 0 point, and we will get that theta bar will just be the theta bar dynamics evaluated at 0 point. And here we go, we found our cotangent values, and this can then be implemented in our AutoDiff engine. Okay, I want to quickly summarize this video because it was quite a lot, and we ended up doing a general derivation and then making a lot of computational tricks. So let me remind you again of what the actual task was. So we have neural ODEs, or in the scientific computing interpretation, the final time integration of ordinary differential equations, which we framed as a wrapper function Q, which takes a set of parameters theta, an initial condition U0, and the length of a time horizon capital T. And then it solves an ordinary differential equation using, for instance, a Runge-Kutta 4-5 scheme by evaluating a right-hand side dynamics given by the function f, which depends on the state u and theta. And now we want to backpropagate cotangent information from the state at the end time to the parameters, to the initial condition, and to the length of the time horizon, which we derived in great detail in finding auxiliary problems that allow us to evaluate the vector-Jacobian products. And we found the full pullback rule here in that we get the cotangent on the parameter vector by solving or by computing a functional inner product between the Jacobian of the right-hand side with respect to theta and an adjoint variable lambda. We found that the cotangent on the initial condition is the lambda value at t equals 0, and we found that the cotangent on the time horizon is just a simple inner product. And in order to get the lambda, we had to solve an adjoint problem reversely in time with a dynamics which we derived to be minus the Jacobian of the original right-hand side with respect to u transpose applied to lambda. And then we made a couple of considerations. We derived an approach in order to do an O of 1 backprop or an O of 1 approach to solving the adjoint dynamics by running the primal problem backward in time as well. But remind you again, this might cause you troubles if you have a chaotic ODE problem. Even if we applied that, we might still have to save the adjoint variable at intermediary points in order to then evaluate the quadrature, but then we derived an auxiliary ODE which performs the quadrature for us. And in total, we then saw that this all can be merged into an auxiliary augmented ODE dynamics, which runs backwards in time. What a long video. I hope you enjoyed it. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. Okay, thank you so much for watching it. If you want more details on automatic differentiation, like how to obtain these vector-Jacobian products, I have videos on that channel, so I encourage you to subscribe to it, and I'm pretty sure you will find something interesting here. Also, consider liking this video. This helps me a lot. Here you will now see similar videos, and I hope to see you in one of the next videos.